Good afternoon, everyone, and welcome to another Quantum Matter Meets Math session. I hope you had a great holiday season, and I wish you all a happy new year. Today, we have the enormous pleasure of having Professor Subir Sachdev with us. I am certain most of you know Subir for his work, but I will attempt to give a short introduction anyways. Subir had his PhD in theoretical physics from Harvard University in 1985. He held positions in Bell Labs and Yale University, where he was a professor of physics before returning to Harvard. Subir has been awarded several honors, among them membership of the American Academy of Arts and Sciences and the Lawrence Chair at Leiden University. He is the recipient of the 2015 Dirac Medal for the Advancement of Theoretical Physics, awarded by the University of New South Wales, Sydney, Australia, for his many seminal contributions to the theory of strongly interacting condensed matter on transitions, including the idea of optical with nationalized theory of high temperature superconductors in cuprates. He was also awarded the Dirac Medal, awarded by the ICTP, jointly with Dan Tan Son and Xiaogang Wen for his contribution towards understanding novel phases in strongly interacting many systems into regional transdisciplinary techniques. It is true to have not physically but virtually. Today, he will tell us about the model of entangled qubits describing superconductors and black holes. So without further ado, I leave you with Subir.
Well, thank you very much, Bruno, for the very kind introduction and for the opportunity to give this seminar. I hope my audio is running well. I had a little difficulty hearing part of the very nice introduction, but I hope the difficulty is not on your side. So please let me know if there's any issues with the audio. Okay, so now I've got to share screen. Okay. All right, so I hope you can all see my screen with the green circle. And as Bruno mentioned in the beginning, I'm happy to entertain questions. Please don't hesitate to interrupt me while I'm speaking. All right, so just to begin in some very simple terms, for physicists anyway, and the central theme of my talk will be the many different physical manifestations of quantum entanglement in systems in condensed matter and also in quantum gravity. And it turns out these very different applications of entanglement also lead to some rather remarkable new mathematical results connecting systems of very different character, and I hope to also describe some of that. Anyway, so sometimes quantum entanglement is referred to as spooky action at a distance, a phrase attributed to Einstein, although I don't think he ever used it. But in any case, what Einstein mentioned was that there were some rather strange features of quantum mechanics that didn't seem acceptable because they implied highly non-local correlations between different measurements. But in any case, acceptable or not, today that this is a well-established characterization of quantum mechanics, and many experiments, including this one mentioned here in the New York Times, have established without any doubt. So let me just define for the more general audience what is quantum entanglement. Well, it's really the idea of quantum superposition extended to more than one particle. So I'm sure you're all familiar with the idea of the double slit experiment, where an electron can be both in the left and the right slit. Similarly, when you have two electrons, they can be in an entangled state, like the one shown here at the bottom, where of the two electrons in a hydrogen molecule, one has spin up and the other has spin down, or vice versa. And the superpositions of these physically distinct configurations then gives you an entangled state. Now, what makes this rather bizarre is that entanglement can be preserved even when you separate the two spins. So if you imagine separating the spins without disturbing their orientation, then if the left spin is up, then the right will be down, and vice versa. So if you measure the left spin and find it to be down here, the other spin, no matter how far away, is still up. It will definitely be up. And this, highlights the kind of non-local aspect of quantum mechanics, where the concept of a quantum state is not necessarily associated with any position in local position in space. It's really an object that doesn't really live anywhere, but determines in this correlations between measurements in regions that could be separated far away. And this is sometimes called the EPR paradox, where the measurement and observation of one particle instinctively determine the state of the other particle. But it's not a paradox. Indeed, it is in fact a fact that has been tested experimentally. Okay, so that's a quick popular summary of entanglement. So what I've described so far is two-particle entanglement. And the theme of my talk is really multi-particle entanglement. So again, keeping things a bit simple and precise, at least in this part of my talk, imagine you have what we now call a qubit. This could be an electron with two states, where the spin is up or down, or it could be any other pair of quantum states. And on this qubit, we have various gate operations that, say, a quantum computer could apply. We call them the X, Y, and Z Pauli gates here, which, the X gate flips you between the two states. The Z gate gives you a phase factor, and so on. And in many physical situations, in particular, like the two electrons in a hydrogen molecule, there is a simple interaction between the two qubits, which can be written in this way. Your X1 refers to the X operator on the first qubit, and so on. So if you take this particular operator and look for its eigenstates, there are 4 eigenstates because there are 4 states with 2 qubits. Then there's the so-called singlet eigenstate that I already showed you, which is the lower energy when J is positive, which is energy minus 3J, which is up, down, minus down, up. Then there's 3 other states which have energy plus J, the so-called triplet states shown here. And these would be excited states of the system of 2 qubits. So the model I'm interested in now, I can define the model that has occupied a big part of my career in trying to understand its properties. Here's the Hamiltonian. Just take a bunch of n qubits. So there's a total of 2 to the n states in your Hilbert space with this spin dot spin interaction. And then you have a coupling between them, this coupling J, which is Jij. So any 2 pairs of qubits are coupled with the coupling J. So for example, you have a coupling J between these 2 pair or that pair or any other pair. They're all to all coupling. And the model we're going to study, which turns, this model as stated is for a general Jij, is impossible to solve. It's just too hard. But if I tell you that the Jij are independent random numbers, then amazingly, you can make a lot of progress in the limit of large n and understand something about the spectrum of this operator. Here's a technical comment. In fact, some of the things I'm going to tell you today are, strictly speaking, not true for this Hamiltonian, because this Hamiltonian ultimately at the very low energies forms what's called a spin glass state where the spins freeze. But there's evidence that higher energies, what I'm going to tell you, is still true. But if you want a precise statement, then a mathematically rigorous statement, then the statements are for a somewhat generalization of this model, where instead of having 2 states per sites, you have m states per sites. And m actually goes to infinity also as n goes to infinity. I won't describe that model, but just for the purpose of the presentation, I'll just describe it in terms of this simpler model. Okay. And there are other models that will have the same physics that I also probably won't describe explicitly. But it's not too much of a misleading statement to say that I'm talking about this model. It's just easier to keep in mind. Okay, so we are interested in the spectrum and thermodynamics of this Hamiltonian, this very simple model. And the claim is this is one of the main results first that I will state and give you just some indication of how you derive it. The claim is that if I compute, say, the partition function of the Hamiltonian as written, in the limit as the temperature is much smaller than the root mean square coupling J, then this partition function can be written in the following form. There's a term here, an overall prefactor, and that's the S is what we call the entropy. And in this particular model is in fact a well-defined entropy as the temperature goes to 0. So it's a universal number, in fact, independent of many details of the model, first computed in this paper with Georges and Parcolet. As we'll see, this is deeply connected to the entropy of, it has a mapping, it isn't exactly equal to the entropy of black holes, or the Bekenstein entropy, Hawking entropy of black holes. Then there's a correction, which gives you various temperature dependence correction to the free energy and also determines the low temperature behavior of many of the observables. And that, amazingly, can be written as a path integral of two-dimensional gravity. And I will show you exactly what this two-dimensional gravity theory is before the end of my talk. So the two-dimensional gravity by itself should be then have an action that lives in two space-time dimensions. But many of the degrees of freedom can be gauged away because there's a reparameterization symmetry in gravity. And when you gauge it away, if you take 2D gravity with a boundary, this is the theory that I'll show you, in the end, the underlying degrees of freedom actually only depend on one coordinate, which is the time coordinate along the boundary, which you can just think of the imaginary time of this quantum spin system. So in quantum mechanics, we know that if you have a quantum system, imaginary time is periodic, runs on a circle of circumference h bar over kBt, and this f of tau is a function of that time. And as we'll see in the gravity theory, this really should be thought of as a time reparameterization. So just like general relativity has general coordinate invariance, this very simple gravity theory on a circle has time reparameterization invariance. And that's really one of the crucial properties of the qubit model that I showed you in the large limit. Okay. So yeah, I guess I've already said this. This will turn out to be the fluctuation of the boundary of a theory of 2D gravity in 1+1 space-time dimension, something I call a boundary graviton. And what this 2D gravity theory is, I will derive in a while. I'll give you an explicit form of this, but you can guess the form of it if you realize that it's really a theory where the reparameterization symmetry is broken down to conformal symmetry in 0+1 space-time dimension, which is the group SL2R. Okay, don't worry if this is seems too technical right now. I will derive some of this at least in a different way later on. But anyway, so the claim that I've made is that this particular Hamiltonian, or really it's this particular variation of it, I could start from this Hamiltonian and turn the crank as a condensed matter physicist, work with this path integral, do lots of changes of variable, and after a sufficient number of changes of variables, I will end up with this path integral. Okay.
Can I ask a question?
Yes, please, go ahead.
Well, I don't know why this happens in the end, but I was wondering, is there a priori reason why you can see that it will be a 2D theory rather than some other dimension from the initial Hamiltonian?
So first of all, of course, the Hamiltonian has no space. So you would say the path integral is a space only over time. So it should be a 0 plus 1D or 1D theory at the best. And so if it's a strongly coupled quantum theory in one space-time dimension, but then there's a holographic principle, which comes from originally discovered in string theory, but now seem to be a much more general principle, that strongly coupled quantum theories in D space-time dimensions have some connection to theories of gravity in D plus 1 space-time dimensions. So that's how the 2 comes here. So in this case, when you turn the path integral, the way you can derive this is like I said, you just write down the path integrals of this theory, and you manipulate and do lots of changes of variable, you'll get this path integral, which is still living in one space-time dimensions. What I will show you towards the end of my talk is you could start from a full 2D theory, in fact, a 4D theory, but when you go to low energies, it becomes 2D gravity. And you can just manipulate and fix various gauges in the 2D theory and end up with the 1D theory. So this is one of the rare cases, in fact, where you can fully establish this holographic correspondence by solving both sides of the theory. Okay.
Okay, thank you. That was very helpful.
All right.
Thank you.
Okay. Okay, but here's the danger sign. This is the technical part for those of you who are condensed matter theorists. How would I even proceed to do this? And this is something that took many years of work, starting with work I did with George and Park-Olay, and then more recently, around 2005, Kitev and Maldor-Sena and Stanford really put in the final places of this connection. So what you do is you take your spin operator and you write it in terms of fermions, where the C's are fermions. Then you introduce replicas to average over disordered. And then when you do that, you get about one-dimensional path integral of these Fermi operators with this all-to-all coupling between replicas. And then you can take this theory and by some Hubbard-Stratonovich transformations and using this identity for a delta functions, you introduce a Green's function of the two fermions. And so this integral over sigma just tells you that, sorry, there should be a dg over here too. So this integral over sigma gives you a delta function between g and this. And then you do the integral over g, that gives you 1. Sorry, I didn't write that correctly. And you plug that in here, you do some changes of variables. This is all relatively standard, the kind of things you do in many different contexts of condensed matter. You end up with this particular action over these bilocal fields, g that depends on 2 times. Okay, and then you notice that the explicit time dependence here is entirely in this time derivative. There's no other time dependence in this theory. And as a consequence, if this term was not important, the rest of the terms are kind of obviously invariant under time reparameterizations. And so the key is really that this term should just disappear at low energies. And that's, in condensed matter, you would say this term disappears because the system is a non-Fermi liquid. These sigmas and g's have some singular dependence on low frequency. And at low frequency, this term is not important. So once you throw out this term, then you see this reparameterization invariance emerging. And then, okay, once you see that, you take a saddle point, which is of this path integral, and then you just look at the fact that at higher energies, reparameterization symmetry is going to be broken. So, and the low energy modes, sort of like a spin wave mode or a Goldstone mode, are just time reparameterizations of the saddle points. So GS is the saddle point solution, and then you take time reparamerizations of the saddle point solution. And you ignore all of the fluctuations in this big path integral. So you convert this path integral over 2 fields depending on, sorry, that should be a tau 2, depending on 2 times each, to just a single path integral. So then that's a complicated calculation of another change of variables. And when the dust settles, you get exactly what I claim. All right, so these are the steps that I'm not going to show you. It's somewhat technical, but I'll show you eventually a different way of getting the same answer. All right, so that's all a formal set of manipulations of this particular model. Now I just want to show you what good is it. So for example, one of the things you can do, if this was sitting in some experiments in Kinet's matter, is compute the dynamic spin susceptibility. So this is just defined by this quantity here, say the X operator between the ground state and all excited states. And you measure the spectral density of such excitations. So this is at T equals 0. There's a well-known expression at finite temperature. All right, so through the tricks I just mentioned, you can actually compute this thing. And I show you here the numerical solution, which is the blue line, and this particular analytic solution. And this analytic solution has some very remarkable properties. First, the leading order term at low temperature is this tanh function. And this is the characteristics of systems that have conformal symmetry. And in particular, the important point about this is that the energy scale J has completely disappeared, doesn't appear at all. And there's a universal scale, which is just determined by the temperature and Planck's constant, which appears here. So the natural dissipative time here is just h bar over kBt. Then there are some corrections that break conformal invariance. And this correction, this term here, is in fact the contribution of 2D gravity. So you can compute it from a theory for 2D gravity. You can compute this correction, and you can see it fits beautifully to the numerical data. And there are further corrections that depend on other graviton modes. So what this gives you is a very complete theory of a non-Fermi, very simple phase of matter without quasi-particle excitations. So it's a very useful connection then, this gravity connection. It tells you all kinds of physical information about this very simple spin model. Okay. All right, so that's the summary of the simple qubit model and some of the things you can do numerically and compared to the theory of, the theory I haven't really shown you what it is. But now I'm going to show you that theory, but I'm going to derive it in a completely different way, where I'm going to turn into a gravitational physicist and show you I'm going to get exactly the same theory. And hopefully by the end, you will see why, because ultimately the key is symmetry, the key is symmetry being time reparameterization symmetry broken down to conformal symmetry. All right. So anyway, questions so far, then any other questions on this result? Okay. So then let me tell you about black holes. Okay, here, you know, everything I'm going to tell you are things I've learned over the last few years. I certainly forgot everything about black holes from my graduate school days. But to begin very simply, a black hole is a solution of Einstein's equation. And any mass, if you take a mass m, then if you compress it sufficiently at a radius smaller than r, which is this quantity you can obtain from the mass, then that object will become a black hole, where classically no light can ever leave from the inside of the black hole and go outside. In fact, no information can be sent from the inside to the outside classically. Okay. So, however, when you start thinking quantum mechanically, the black hole horizon is not completely opaque, as was first argued by Hawking. And in modern terms, you would say, imagine you take this qubit, an entangled pair of spins, and separate them by putting one on the inside of a black hole and the other on the outside. And quantum mechanics stays they're still entangled. So then a measurement outside the black hole then determines what happens inside the black hole and vice versa, at least in principle. However, you know, if you're sitting outside a black hole and you have this qubit in your hand, to you, this is not really an entangled bell pair with another qubit, because you can never ever communicate this directly with the other qubit inside the black hole without jumping in the black hole yourself. So as far as you're concerned, this is just a random qubit. And a random qubit really means a thermal mixed state. So it has an entropy and a temperature. So that was Hawking's observation that all black holes have a certain temperature and also corresponding entropy. So this I call the Bekenstein-Hawking entropy and the Hawking temperature. The entropy is proportional to the surface area precisely because you can think of it as the entanglement entropy on the surface of the black hole horizon. There's another interesting feature of black holes, which comes from combining solutions of Einstein's equations with Hawking's expression for the temperature, which is that if you were to perturb a black hole, that is, for example, you threw something into the black hole, another star fell into this black hole, then the two objects would, move around for a while, but eventually the black hole would come to rest and become a featureless sphere with a slightly bigger mass. So you can ask, how long does that process take? And that time turns out to be very simple when you think in terms of the Hawking temperature, just h bar over kT. So this dissipative time that appeared over here, so this is the first connection that there's some connection to strongly interacting quantum systems without quasi-particles, because strongly interacting quantum systems, as I showed you here, also have the same time, h bar over kT. So there's a universal time in which strongly interacting quantum systems equilibrate, and that universal time also appears in the equilibration of black holes. So they're sometimes called the Planckian time. Okay, but there's actually a much more explicit and deeper connection, but that was one of the first indications that there was something similar here. Okay, so now let me take a particular solution of a black hole, which I will then argue is in fact related to the spin model that I introduced earlier. So we take Maxwell's theory of electromagnetism and Einstein's theory of general relativity, and we look, and this allows solutions of black holes with a net charge. Now, as far as we know, all the black holes in our universe are neutral, but okay, let's consider this case. Now, it turns out if you look at the solution, it's the so-called Reisner-Nordstrom solution, that as you approach the horizon of a black hole, and this radial direction I'm going to call zeta, and zeta will be 0 right at the black hole horizon. And then what happens is if you look at just the Einstein's equations, they kind of decouple. That is, the decouple along the physics around zeta decouples with the variation along x. So in the end, when you are very low energies and right near the horizon of a black hole, you can just think of it as a one-dimensional gravity theory. So you end up with a theory of gravity in Einstein's general relativity for charged black holes, which is in 2 space-time dimensions, 1 dimension zeta and time. So that's one reason for actually saying that it's not completely ridiculous to consider gravity in 2 dimensions. It in fact appears as the low energy theory of a physical black hole in 4 dimensions, space-time dimensions. So it turns out, and this is what I'm going to give you some derivation of in a way, that the 2D gravity theory you get near the horizon of a charged black hole in this Maxwell-Einstein theory is in fact exactly the 2D gravity theory that appeared in the qubit model, or its cousin, which is sometimes called the SYK model. Okay, so now let me actually show you this computation. I'm going to show you all the steps. Some are a bit technical, but really what I'm doing now is quote unquote elementary. It's something that could have been done, it's just classical physics with a little bit of semi-classical fluctuations put in. It could have been done 50 years ago, but curiously, it wasn't done until about 5 years ago because there wasn't any motivation, and because the quantum side of the theory, the fact that this 2D quantum gravity theory made perfect sense as a quantum system was not appreciated. until this connection had been made. So I start with Einstein-Maxwell action. So what are the terms here? Well, this is the Riemann curvature tensor. Sorry, the Ricci scalar, which is made from the Riemann tensor in d plus 2 dimensions. Little d will be 2, so that I'll be working in 4 space-time dimension, which is r dimension. G is the metric. This is the Ricci scalar made from the metric. This is just a constant, which is called the cosmological constant. We choose to work with negative cosmological constant because things are a bit simpler at infinity then, but you could also work, you can make this as small as you want and everything I say will still go through. And this is the Maxwell theory, F mu nu. This G is some electromagnetic coupling constant, alpha, and this is kappa is related to Newton's constant. All right, so we're just going to write down the equations of motion of Einstein and Maxwell in free space, in empty space. And where is the charge? Well, the charge is really sitting at the very center of the black hole, where we're not actually going to go. So this gives us a boundary condition that as you go to infinity, there's an electric field by Gauss's law, which is the charge divided by 4 pi r squared. And similarly, there's a boundary condition of a certain, there's a mass at the center of the black hole, and that tells me something about the boundary condition in infinity. Because of this cosmological constant, it's not going to be Minkowski spacetime. It'll be ADS2 spacetime, ADS-D plus 2 spacetime. But okay, that's not a really that important difference because I can make this ADS2 curvature as small as I want. Okay, so these are the differential equations you have to solve. Okay, that's it. You just take, today you can plug these equations into some mathematical program and it will solve them for you. Well, with some help. So we're going to assume spherical symmetry, and that simplifies things a great deal. And then you just get some differential equations, which turn out can be solved exactly. And then after you solve them, found the classical solution, then you have to do a path integral over all metrics and gauge fields with the same action. That's the prescription of how you quantize any theory. And of course, this is far from a precise prescription because there's all kinds of infinities here and general coordinate invariances and gauge invariances that you have to deal with. So nobody really knows how to evaluate this path integral as defined. But what I'll show you is that in a certain low temperature limit for charged black holes, this can be actually today exactly evaluated in this low T limit. The full, just this particular gravity theory. Not to say that it makes sense at high energies, but there, yes, please go ahead.
Are you working in Euclidean signature?
I'm trying to remember. I'll go back and forth, but yeah. So this certainly is for Euclidean signature here. Okay,
because also in the action you have used root of G instead of root of minus G.
Yes, correct. Thank you. Yeah, this is Euclidean. I'm pretty sure everything is Euclidean. I tried to be careful about that from what I remember. Okay. So first, let's look at the saddle point of this path integral. So there's the action. We just write down the Euler-Lagrange equations, and this is the solution right here. So this is the metric in 4 space-time dimensions. It's spherically symmetric, so only depends on time and r, the radial coordinate. And this is the gauge field. So this is A is only as a tau component, so there's only an electric field. There's no magnetic fields. And there's various parameters here, mu, which is a chemical potential, which is conjugate to the charge, and there's a mass, which then determines the location of the horizon, and hence the temperature by Hawking's formula. So this is roughly what it looks like out at infinity. It's just almost empty space with nearly flat, with some negative curvature because we are in because of this cosmological constant. And then there's a horizon space kind of shrinks, and then there's a horizon beyond which there's a black hole. All right. So this horizon appears when this V of R has a 0. So this particular expression has a 0 at some R, and that's where the horizon is. So we're going to now zoom in to that horizon and look at what the metric looks like in this vicinity. So,
Question?
yes.
Is in the expression for V of R, the third term, should that be a Q instead of a theta? I mean, what is this theta? I didn't catch that.
Okay, sorry, yeah, not defined here. I will refer you to actually not this paper,
Okay,
which has
sure.
a different
No issue.
notation.
Thanks.
I will refer you to this paper. I'm sorry. Thank you for pointing that out. There's something that's not defined. It's some combination of Q and M, if I remember right. Yeah, I think
Okay,
it's related to Q. It's related to Q in some way. I've forgotten. Thank you. I'll fix that. Okay. Yeah, every time I give this talk, some other error that nobody else noticed. So I have a good audience. I've already found several errors. All right, so I guess I call the location of the horizon R sub h at 0 temperature, and then I define a coordinate zeta, so that when sorry, which way is it? Yeah, zeta goes to 0, then I'm very far away. No, zeta goes to 0. Sorry. Which way is it? I'm sorry. I thought zeta goes to 0 was right near the horizon, but that doesn't seem to make sense here. So I guess zeta goes to infinity is where I'm near the horizon. And yeah, okay. Zeta, yeah, R goes to RH. Right, okay, sorry, zeta goes to infinity. I'm sorry, I've forgotten that. Yeah, all right. And R2 is just some parameter. So you just do this change of variables from R to zeta, and then you go right near the horizon where zeta goes to infinity. Just look at this expression. And when you look at that expression, it factorizes. So there's a part here that only depends on the radial direction and time. And then there's a part here which is just the spherical round metric, the sphere. So this is the radial direction, angular direction when nothing much is happening. And so you have a theory here where space-time is two-dimensional with this metric minus dt squared d zeta squared over zeta squared. And this is what the vector potential also depends only on zeta. It's some constants that are all specified here. So here's a summary of that picture. So what's happened is right near the horizon, then the metric now got Euclidean time, Minkowski time, sorry. D zeta squared minus dt squared over zeta squared. Dx is the transverse direction. So here's a two-dimensional space-time, and there's some electric field on the surface of a black hole. And right, yeah, zeta goes to infinity. Sorry about that, right at the black hole horizon. Okay, so we have a theory of two-dimensional gravity with this Minkowski, with this particular metric, which is called ADS2, and the S2 is this factor dx squared. Okay, so in the remainder, we're just going to throw out the x2, but not completely. We will have to worry about it a little bit because to make sense of this theory, we do need to worry about the fact that it's embedded in higher dimensions. Anyway, so from this metric, you can compute the area of the horizon, and from Hawking's formula, the entropy of the black hole. And you can do this with different charge. And what you find when you do this is that the entropy depends on the total charge in a very specific way. And this is a formula that you can derive from Einstein-Maxwell theory. You can derive this expression, as I showed in this paper. But amazingly, you can derive this expression also, where E is defined in some way that's related to this electric field that's completely well-defined, which I haven't shown the details of. You can get the same relation also from the SYK or the spin model, just by various manipulations of the path integral that I showed you earlier for the spin model. So this was really the second indication that there's some deep connection here between the black hole and the spin model. Not only do they this Planck dissipation time matches, but also quantitatively there's a match in how the entropy depends on the electric charge. Okay. All right, so now that we have this metric, let's try to understand a bit better. So now I go to Euclidean time. And Euclidean time, you write it this way. And this is the metric shown right here. It's the metric of hyperbolic space. It's the simplest, in fact, the first metric discovered which had any negative curvature, or Lobachevsky's, I guess, in the 19th century, shown here in this famous picture by, what's his name? Sorry, I don't remember. Okay, so this is the metric here. And this metric has a very beautiful symmetry. That is, if you perform this fractional linear transformation, A, B, C, D, in this way, then in the new coordinate tau prime and zeta prime, the metric has exactly the same form. So this is an isometry, and this particular transformation is called SL2R. So this is very analogous to the group SO3, which is the symmetry of the sphere. If you write down the sphere metric in some theta phi coordinate, it doesn't look spherical at all, but it does have a symmetry. In fact, SL2R is some kind of non-compact version of SO3. Yeah, okay. So, and that's just the group of fractional linear transformations with unit determinant. It's also the conformal group in 0 plus 1 dimensions if you extend it from higher dimensions. And that's the symmetry of this ADS2 metric. So what we have then is the following phenomena. We started out with a gravity theory where the action was invariant under time reparameterizations. In fact, independent under general coordinate invariance. Then we found a saddle point. The saddle point is a given metric, which is not fully invariant under any reparameterization, but it's invariant under SL2R. So this is, sort of like if you have a ferromagnet. In a ferromagnet, you have full rotational symmetry in the Hamiltonian, but when you take a ferromagnetic ground state, the spins all point in one direction, and then the invariance is only rotations about one axis. So you break, SO3 symmetry down to U1. So here it's exactly the same idea. You're broken down time reparameterization symmetry down to SL2R. These are much bigger groups, but the idea is very similar. So therefore, if you want to write down the low energy theory of fluctuations, what you have to do is to write down what the analog of what we call a sigma model. We just have to take the SL2R symmetry and apply it and rotate it to the saddle point. So you take the saddle point and you rotate it away, and you look at how much that rotation costs. And the reason that rotation costs some energy, because here the time reparameterization invariance, at least the two-dimensional time reparameterization invariance, is not exact because you're embedded in this higher dimensional space-time. Okay. All right, so this is the claim. And so now what we have to do is, in principle, relatively straightforward. We have a saddle point, but the solution of the Euler-Lagrange equation of the action, here's the solution. Now we just have to look at small fluctuations of it. So it turns out, and this is where, the brilliance of gravitational physicists, including Maldacena and Stanford, comes in. It really becomes a question of finding the right coordinates. And this is all, not as simple a choice as you might think, because there are all these symmetries here and redundancies associated with general coordinate invariance and gauge invariance. And you have to find, and a lot of those directions give you infinities, but those infinities are meaningless because they just associate with changes of things that are not physical. They're just choosing different coordinates for the same physical phenomena. So you have to find the right choice of variables, which gives you, physical excitations, and then argue that everything else is pure gauge, and so can be just ignored. And the right physical variable turns out to be what you can call as a boundary graviton. So there's this, at very far away from the black hole, your metric is ADS4. Near the black hole, it's ADS2 cross S2. And the purely two-dimensional gravity theory, in some sense, is trivial because there is no graviton in 2 dimensions. You can gauge it away completely by just coordinate transformation. So there's no graviton excitation in 2 dimensions. However, when the 2-dimensional becomes 4-dimensional, right at the boundary, there turns out to be a low energy excitation, which is physical. And so the first correction to the saddle point is just given by the fluctuation of this boundary graviton. And if you just focus on that sector, you get a perfectly well-defined theory. If you ask something about higher energy, then you will have to go deeper into 4 dimensions. And in 4 dimensions, nobody knows how to define this theory because gravity is non-renormalizable, and you probably have to embed it in string theory to make sense of the full theory at all energies. But if you just focus on the boundary graviton, everything is well defined. All right. So here's the result when you do that. When you just take this action and then find the right variables, you'll find that the answer is equal to this. And this particular path integral here, where is it? You can basically, by changes of variables, take this path integral and write it as just a one-dimensional path integral, and the one-dimensional path integral is just telling us about the fluctuations of this curve here. It's the coordinate along that curve, and the action for that turns out to be f of this 2D gravity action. And what is it? So I can show you what it is now. Finally, so
can you?
Yes.
Can I ask a question?
Yes.
So I thought the Goldstone modes are general reparametrization f of tau, but modded out by SL2R.
Correct. Yes. So this particular action will be 0 for SL2R transformations.
So f of tau is a general reparametrization of this theory, but somehow.
But if f of tau belonged to SL2R, this action will be 0.
Oh, I see. Okay.
So you have to mod out by that. Okay. So this really, the action is df of tau mod of SL2R.
Okay, thank you.
I mean, it's like in a ferromagnet, there are some rotations, like in this direction, that cost you no energy, but of course that integral is just 2 pi, so you don't worry about it in general. Mm-hmm. But here, SL2R is an infinite group, so you do have to worry about the fact that
that's why I'm asking.
Yes. Yeah.
That's why I'm asking
so
why there's
because it's right. So there's a symmetry here which is non-compact. There's a non-compact symmetry, and you do have to mod out with the volume of that non-compact group.
Okay, thank you.
Yeah. Anyway, but that actually connects directly to what I was going to say. So what is this action? Well, the action has to be something which is 0 for any SL2R transformation. That is, if you take any transformation f of tau, which is a tau plus b over c tau plus d, that must give you 0 action, because that SL2R transformation just takes the ground state back to itself. Just like in a ferromagnet, rotating about this axis gives you no change in energy. So you have to write down an action which is invariant under SL2R. And this turns out to be exactly the defining property of what's called the Schwartzian. So this particular combination of derivatives looks like a horrible thing. But if you take g of tau equals a tau plus b, then it's 0. And also if you do a SL2R transformation on an arbitrary g of tau, it doesn't change its value. Okay, and don't worry about the tan. The tan has to do with going from 0 to finite temperature, going from a line to a circle. It's just a technical detail. So anyway, so if you do this procedure and you just look at in principle, as I said, this could have been done 50 years ago if anybody had been brave enough. That you take the saddle point and just really work really hard and find the right set of coordinates in which you can fix all the gauges and all the infinities having to do with symmetries and so on. Then you would end up with this pattern interval. And so that's now been done. And amazingly, this is exactly what you get also for the SYK model. And for very similar reasons. There also you have a time optimization symmetry, which I showed you for the path interval. And the saddle point has a conformal invariance. I didn't show that to you, but that's also quite easy to see from that particular action and its solution that we found a long time ago. All right. And now today, this particular theory looks really horrible, but it in fact doesn't even look finite because it's not even positive definite. But a lot of the non-finiteness has to do with this non-compactness of the symmetry because you have to mod it out by SL2R. And once you mod that out, this integral can be evaluated exactly. And in fact, there's all its correlation functions are known exactly. And there's some very deep results. There's very clever ways of obtaining this using supersymmetric ticks by Stanford and Witten, or you can use something called the Bustermat-Heckman formula in pure mathematics. Anyway, so now you can play with this and get all kinds of results. And this has physical consequences for the spectral function of chi of the spin correlations. I didn't show you those consequences, but they also have been computed. Okay. All right, so this is the derivation. If you want to see a few more details, how am I doing on time? So I have now written down the main result. I don't have a clock in front of me. 12:53. Okay, so I have about 10 minutes or maybe less. Okay.
Yes.
All right, then I'm like, I can put these slides on my website. You can see them. So this is the danger sign. So this is just showing you how you go from 4 dimensions ultimately down to the 4-dimensional gravity all the way down. You change variables in some inspired ways, and you end up with this 2D, with this Schwarzian action. So what you do, first of all, I can at least show you how you go from 4 down to 2. You just take radial coordinates. So you have a 2-dimensional metric, and then a field phi of r. Okay. And then, yeah, okay. And then you put this particular ansatz into the 4-dimensional Maxwell's action, and then you end up with a 2-dimensional theory, just depending only on the radial coordinate zeta and time tau, and the angular coordinate just completely gone in this here. And now this is a theory called Jakiv-Teitelbaum theory. It's the Einstein action, R2, but there's also a scalar field phi, which determines the coefficient of the Einstein action and also the Maxwell term. And all of these are explicitly known as you go down from 4 to 2 dimension. So you're down from 4 to 2, then you take the neo-horizon limit, and you further simplify the 2-dimensional gravity, and then you realize that you can fix the gauge by fixing the boundary metric, and then you choose your bulk coordinates to be some time parameterization along the time direction and zeta along the radial direction. And to fix the boundary metric, the length of the boundary, you fix that, and that fixes zeta as a function of f. You plug it all back in into Einstein's action, do a lot of algebra, and out pops this particular result. I should say this was all essentially outlined and derived by Maldacena, Stanford, and many other gravitational physicists. All I did in this paper was to put it all together in one combined treatment, starting all the way from 4 down to 2, down to 1. It was done in bits and pieces in various other papers. And it took me a while to put it all together, so I thought it'd be useful to write it up. Okay, so that's the main result from which you can compute lots of things. All right, so I think I have completed the main part of my talk, which is I started with a simple qubit model and showed you some of its properties. And then I started with Einstein theory and showed you that, in fact, you can derive a common path integral that connects them up. And this connection, these in the last couple of years has been very, very useful, it seems, as an observer to me anyway, in all the recent developments on the Hawking information paradox and which are all been, checked or inspired in some ways with the SYK model, but now, well, actually, a lot of it is really expressed in terms of the 2D, just to keep Teitelbaum gravity theory, and people can now understand, I think, much better how the entropy of a black hole evolves as it evaporates. And I guess the contribution of the SYK model would be that I would say it's fair to say that nobody took 2D gravity to be any reasonable, sensible theory of anything of a fully quantum mechanical system until this connection to the SYK model was established. Okay, now in the remaining 5 minutes, let me tell you about what I really work on, and with some speculative connection. This will be rather quick. So this is yttrium barium copper oxide, the famous high temperature superconductor. So here's a picture of it anyway. Okay, there's a piece of YBCO floating over some magnets, and the physics of that has to do with electrons hopping on this layer of square lattice of copper atoms. And you can write down, and you can think of the physics as starting from a square lattice of qubits, which in the natural state in lanthanum copper oxide form this so-called antiferromagnet, where the spins are not entangled, but just correlated in this way. And then you remove some of the spins and allow them to move around. And we believe that much of the basic physics is understanding the motion of these holes in the background of the spins. And so from that, you get a rather complicated phase diagram, which have been studied for 3 decades now, with many different phases. My particular attention in the next few minutes has to be on this so-called strange metal, which has some connection, at least it's one of its defining features, is the absence of quasi-particles, that it doesn't have any well-defined excitations, but it, in many respects, looks rather like the SYK model in the sense that all the excitations are rather incoherent and characterized by this universal dissipation time of h bar over kT. So I'm not going to attempt to solve the original model in any sense. Of course, that would be impossible. I wouldn't be spending our time on anything else if I'd solved that model. But here's the model you'd like to solve. Now you have to introduce fermions, which anti-commute between different sites. And this was the model I showed you earlier, so just the SI.Sj. But now you also have fermions, which can move around, which anti-commute. So there are 3 states on each side, either an empty state, up or down. And these are, the commutation relation between various operators. So this particular is the fermion hopping, which moves this empty state around. So really, this one slide completely defines the problem to a mathematician. You could then go back and try to solve it, but I'm sure that's too hard. However, the problem that we think we're starting to make some progress on is the case where these T's and J's are just random numbers. So we'll just take, we were able to make so much progress in this model alone with just J or J random numbers. So let's take both of them random numbers. Okay, so in this problem now you have n sites, not on a square lattice, but just not even in space, but just some n sites. Some of them are spins, some of them are empty, and the spins can move around so that the empty site shifts, and the amplitude for that is random number t, and then the spins can exchange, and the amplitude for that is a random number j. So that's the problem. Can you solve this problem? Okay, so we can't really, but we are making a lot of progress by using numerical methods and also these large M expansions. Yes.
So the thing is that these spins are not in any lattice or in any background space-time, right?
Correct. Right.
So then how do you define the notion of the spin at one site and relate it to the notion of spin at another site? Right. I mean, because there is no frame that is shared by all the sites.
Right. So yeah, so that's not a difficulty. That's because this is, I'm using spin here, but really, if you want to think in your term, think of it isospin. It's really a flavor symmetry. It's not a space-time symmetry as in the Dirac equation. This is non-relativistic physics. And in non-relativistic physics, spin is just a flavor symmetry. It's an internal symmetry. It's not a space, nothing to do with angular momentum. Okay, so just think of it as some isospin. Yeah, because we're non-relativistic.
Okay.
Yeah. I mean, there is a difficulty when you consider spatial quantities like conductivity. Conductivity has a spatial index. Then it's not so clear how you define it. But we have ways of doing it. But since I'm running out of time, I won't talk about it. Just say you can take a different model where you take a high dimension of space. And then there's a very clean way of defining the conductivity. And we just use the same expression here. So there's some tricks you can do to even define things like thermal conductivity, longitude, and electrical conductivity. But there's no problem with spin. With spin, everything is straightforward. All right, so I've just shown you here very recent work with group at Flatiron, Antoine George and Alexander Witek, and my student Henry. So what we computed was exactly the spectral function I showed you earlier for the SYK model. This is now done for the physical system on this random cluster. And what you see is, in fact, this is the zero temperature result. So what you see is that at zero doping, where there are no holes, there's a big peak here. And that's the spin glass state that I haven't really discussed. And it's a very weak, if you look at the strength in this peak, it's rather small, but so there is small spin glass order present at zero doping. But once you dope it, eventually the spin glass order disappears at some critical doping around 0.4 or 0.3. And if you look at the spectrum at the critical doping, it beautifully matches this SYK model prediction, along with this linear term at small frequency, which is the contribution of the graviton. So, okay, this may be a rather strong claim, but anyway, there seems to be some tantalizing evidence in this particular random model for SU2, not for SUM or anything else. So all we've done, taken the model for the cuprates and replaced the square lattice by this random cluster. And the claim is that you get a lot of features that A, look quite similar to the experiments, and B, also to the physics of the SYK model. Now, I'll take a whole another talk to describe all of that, which I don't have. So I'm just going to end. So the simple qubit model that I began with, just randomly coupled qubits, has a connection to the 2D gravity theory at low energies of charged black holes, and also some connections to this criticality near optimal doping in the cuprates. Thanks a lot.
So let's thank Subir for the wonderful talk now. Thank you very much. Okay. Now it's time for questions.
I have one question. Okay.
Go ahead.
Sure.
So regarding the large N derivation,
yes.
So the saddle point equations at large N, they don't break these conformal invariants, I guess. So it's the corrections that break, if I understood correctly. How could you guess? I mean, because I think in the Parkley and George case, this is not true. I mean, there is conformal invariance in that case. So how could you get it that some models break it and you see it numerically, or you can get it? There's some
no. Everything I said applies to the Parkley and George case completely. In fact, they did some of it first. So let me go back here. Right, okay. So there's really two different symmetries you have to keep in mind very clearly. And this is what Kitaev clarified, I should say. I mean, a lot of the pieces were there before Kitaev, but he put them together in a beautiful way. So let's see. Share screen. Yeah, so you can see my screen here. Okay. Right. So this is the full path integral at this point. You have a path integral over two fields, G and sigma, which are bilocal in time. They depend on two times, and this is the complete action. Okay, no approximations whatsoever. You can start from the SYK model and just derive this form. So now we're just going to manipulate this bilocal path integral. So first thing is you look for saddle points. And unfortunately, I didn't write down what the saddle points are. Well, I have it in a different talk since I'm Zoom. Let's see how well I can adapt. Okay. All right. Yeah, okay. So here's a more careful discussion of it. Okay, you can see this this file too, right?
Yeah.
Okay. So you take the saddle point of that action, no approximations, and then you find these Schwinger-Dyson equations. So now at the saddle point, you assume that things only depend on differences of time. So there's only one time and one frequency to consider. This is just the Dyson equation, and this is, well, let's call it the SY equation because we wrote it down first, sigma is G cubed. All right, so now we have to solve these equations, and what you find at low energies is that G of Z is 1 over square root of Z. Okay. Now, all right, so that, and then when you do the solution, what you find is that in obtaining this solution, 1 over square root of Z, these two terms are not important. Okay. So when you throw these terms away, then if you look at the, say, the Dyson equation, but you can look at the same thing of the, you can just look at the same thing at the level of the saddle point of the action. So if you throw these terms away, then these two equations you can write in this form. And now you see there's no time derivative anywhere. And these equations are explicitly time parameterization invariant. So one has to very carefully distinguish two things. One is time parameterization symmetry, which is only approximate, and it's only true when you throw these terms away. Okay. And you have to distinguish that from conformal symmetry. Conformal symmetry is something different. Conformal symmetry is the symmetry that tells you, for example, that if the solution, I haven't written it down here somewhere. This is, yeah. So if the solution at 0 temperature was 1 over square root of tau, which is 1 over square root of frequency, the same thing. I'm sorry, I don't have it here. So this is the solution of the saddle point at 0 temperature. Then these equations also have a, have a subgroup of the transformations of the time parameterization transformation, which is the conformal transformation. The conformal transformations are, well, they map a circle onto itself by a fractional linear transformation, or they map a line to a circle by this tan transformation. And what this gives you is the solution at finite temperature from the solution at 0 temperature, something we are very familiar with in conformal field theory. So this thing, which is 1 over square root of time at 0 temperature, then it's 1 over square root of sine the time at finite temperature. Ignore that factor there. Okay. So that's the conformal symmetry. It's the global conformal group, not the time parameterization symmetry, which is the local conformal symmetry. So the saddle point itself, the saddle point solution is invariant. The low energy saddle point solution is totally invariant under global transformations, but it's not invariant at time parameterizations. And the reason it's not invariant is you can almost see from here. So time reprioritization is kind of a bit of a fake, at least at the saddle point. So if you look at this time reprioritization symmetry, it acts on the two times separately. Sigma 1, sigma 2 are both functions of tau, which is tau 1, tau 2. Now the saddle point you want is a function of tau 1 minus tau 2. Now if you do this transformation, a function of tau 1 minus tau 2 will not be a function of sigma 1 minus sigma 2. So even though these equations are time reprioritization invariant, most of the saddle point solutions are unphysical. They take you from solutions that are, there are infinite number of solutions to this equation. Most of them are unphysical because they will not be functions of tau 1 minus tau 2. So you pick so in some ways, the fact that there's an I omega term and the fact that your time, there's something else that tells you that the whole theory is time translation invariance. You have to just remember that, even though that's not a property of these equations. So that tells you that you have to pick out solution. The symmetry of the vacuum is not time reprioritization, it's the global conformal group. Okay, I don't know, I hope that clarified.
So maybe just to clarify, so how would I guess what is the form of the second term from only this, I mean, the form of the term that you wrote as a action of 2D gravity from only this information? Could I guess that term?
Yes. So what we know is that so this is exactly the argument here. Okay, so you have some saddle point solution, which is tau 1 minus tau 2. Now, when you do a time reprioritization, you don't get the same function, you get a different function. So that would be like taking a ferromagnet from here and rotating it. That's not really a symmetry of the vacuum, that's a symmetry of the action. So GS of tau 1 minus tau 2 will lead to a function of G tilde of sigma 1 minus sigma 2, which will be a different function of sigma 1 sigma 2. So what I want is GS of this G tilde should be equal GS. So I have a more restricted condition. So what I do is I go from G to G tilde, and then I demand that G tilde equals G, which is a second condition. So when you do that, then you find it's only true for this particular transformation. Only for these transformations does G tilde go back to G. Okay. So that's like in a ferromagnet, it's only U1 rotation that take you the saddle point back to itself. So this is the saddle point, invariant of the saddle point, which is different from the invariance of the low energy theory. Yeah, I should have just said that at the beginning. I think that's the question you have. Yes.
But I have to give some energy to the other configurations that are not these ones, and so these
right.
This
so now
has
you
a form.
so
and
so
can
now
I guess
you
that
simply
form?
have yes. So now you say, okay, I have some function of f of tau. That function of f of tau must vanish for all f of tau equals this. With that requirement, you will get the Schwarzschild. The Schwarzschild is the simplest function with the fewest derivative that has that properties. Okay, so I mean, it's exactly what I did here. Oh no, that was a different talk. It's exactly what I did here for the gravity theory.
And the coefficient that I put in front, this is fixed by.
No, that's the hardest part. We don't know the coefficient. The coefficient you have to do some. In fact, today we only know the coefficient by numerical calculation. You have to numerically diagonalize the whole thing and get the coefficient. For the gravity theory, for Einstein gravity, in fact, you can get the coefficient. And that's kind of what I did in that paper. I got the coefficient precisely, starting from Einstein gravity and no fudges anymore. I got exactly the coefficient, this gamma. And that was the purpose of the whole calculation, was to get that gamma. But for the SYK model, we don't know how to get that coefficient. Even for the large n limit, we do not know the value. It's only been deduced by numerics. You can get it in something called the large Q expansion, which is yet another expansion parameter. then you can get the coefficient in the 1/q expansion. But it's only known today by numerics. But the beauty is you can determine it, for example, so this is in fact a test of that. So this C over here that I showed you, this number C, which is a pure number, that depends on the coefficient. So you can do two different calculations. You can compute the specific heat, you can compute this quantity, and you can look at the value of that number. And the whole consistency of the theory tells you get the same number by these two different ways of doing it during the numerics. And that works out beautifully. That's been checked by many people and many different observables. There's like a library of 4 or 5 observables. All of you give you the same value for this coefficient. So that tells you that the theory is correct. Yeah.
Okay.
But no one has an analytic derivation of that coefficient. Yeah.
So more questions? If not, I perhaps have a maybe silly question. I don't know. So in this gravity description, you have this charge Q. Is there a dictionary between what the charge Q means in the original spin model?
Yes. So in the SYK model, it is literally the number of electrons.
I see.
But if you want to work in the spin model, so I remember I had this technical comment here. You have to go to group SUM. And in the group SUM, these spins form a representation of SUM.
Okay.
And so each representation of SUM is labeled by Young tableau.
Oh.
And it's the number of rows in the Young tableau. And that relates to the charge Q of the black hole.
I see.
Yeah, so there's a connection there.
Great. So any more questions?
So I can continue with this one. So
Sure.
Now if you go back to the works of Pacollet and George, let's say and look at as a model that is not that has no randomness, you can also derive the same as a similar theory for the model that that you have looked at.
So what model are you thinking about?
I mean some Kondo-like critical
for the Kondo
model.
lattice model, no, this theory does not apply to the model. So this is actually the key difference between multi-channel Kondo problem and SYK models. They have some formal similarity, but all of the physics I told you about, like the Schwartzian, it does not apply to the Kondo model. And the reason is the following. The Kondo model, in fact, does not have reparameterization invariance. And why is that? So if I don't have a slide with this, I should have had my laptop. Okay, so let me try to say it in words. So, we have this action here where I've integrated out all the underlying spins, and I have this action which, once I throw out this term, has no explicit time dependence. Now, for the Kondo model, you have a bath, you have a bulk. So you write down some action for the spin and its Green's function. You have to integrate out the bulk. When you integrate out the bulk in some sense gives you a preferred time frame on the boundary. From the bulk, you get a tau1 minus tau2 to some power long range interaction. 1 over tau1 minus tau2 squared or something like that. You get some interaction of the spin on the boundary coming from integrating out the bulk. That is invariant under global conformal transformations of both the boundary and the bulk, but it's not invariant under time reparameterizations because there's a preferred time frame that is set by the bulk. And so once you have that preferred time frame, you don't have the Schwartzian mode. So there's this zero mode that comes from the Schwartzian, which is not present in the multi-channel Kondo problem. Yeah. And it's very much tied to, I don't know if you work on DMFT and things like that. It's very much tied to the fact that here, there's a self-consistency condition, which is very different from Kondo problem, where you don't have the self-consistency. Another way to say it, in the Kondo problem, there's a given bath, and then you have a spin. So there's no self-consistency condition relating the bath to the spin. However, when you do this problem, or more general in DMFT, you have a spin coupled to a bath, but then the bath is made up of the same spin, so you have to close the circle. It's because you're closing that circle in a non-Fermi liquid, but this term is not important, that you get the time reparamerization symmetry. In DMFT, you also close the circle, but this term is actually important. You can't throw it out. And that's why there's no reparamerization in DMFT, unless you go to some critical points, which you would then find actually reduced to the SYK type critical points, I believe. Yeah.
Subir?
Yeah.
So I have a question. So what property of the, what symmetry, is there a reflection of some of the symmetries that you talked about that results in the zero temperature entropy, the prefactor in front of the Schwarzschild action? Like, can you just comment on where that term comes from? The overall prefactor? Yeah, that one.
I would say if we don't have a deep understanding of it, what these states are, it's...
No, I just mean maybe less deeply, just mathematically. What, you described the solution. So,
yeah.
And you focused on the aspects of the solution that leads to the second factor, the Schwarzschild.
Right.
But
yeah. So the simplest way that I guess you'll relate to, if you have some scale invariant theory in D dimensions, you know that the free energy scales as T to the D plus Z, okay?
Okay.
Or no, T to the 1 plus D over Z, sorry. T to the 1 plus D over Z.
Yes.
Right?
Yeah.
So or in other words, the entropy scales is temperature to the D, where D is the number of spatial dimensions. T to the D over Z, sorry. Yeah. So this is a model in 0 dimensions, so the entropy is a constant. So there's a universal free energy. We know that there's universal contribution to free energy of any conformally invariant critical point in D dimension. This is the famous, I guess, Fisher-Dijen correction free energy. If you take the 3-dimensional IZ model's critical point in a system of box L, its free energy has a universal contribution, which is a number divided by L cubed, right?
Mm-hmm. Okay.
That's the universal free energy density of any, say, Wilson-Fisher fixed point. In 3 dimensions, it will be 1 over L cubed, the free energy. So now, if you try this function of temperature, is temperature cubed. The free energy is temperature cubed, so the entropy is dF dt, which is temperature squared. So now you go to 0 dimension, where you're 1 space-time dimension. Then the free energy is temperature, and therefore the entropy is temperature independent. So that universal Fisher-Dijen free energy becomes the universal entropy of this model. So this, again, this number S0, in fact, is a pure number which, like a critical exponent, only depends on a few things, like your symmetry group and representation, and that's about it. It's otherwise universal. It doesn't depend on the microscopic Hamiltonian at all. So it's like the universal free energy of a conformally invariant critical point, but in 0 plus 1 dimensions. The hard part is, previously people didn't know of any strongly coupled conformally invariant critical point in 0 plus 1 dimensions. There were things like multi-channel Kondo problems, but they weren't strictly speaking by themselves in 0 plus 1 dimension. They're on the boundary of a system in higher dimension.
Mm-hmm. Okay, thank you. Thank you.
Sure.
So I think it's, if there are no more questions, let's thank again Subir for the wonderful talk and for answering all these questions. Thank you so much, Subir.
Thank you very much. Really enjoyed it. Thank you.
Subir, could you please send the slides to Bruno?
Yeah, absolutely. Yeah, I'll do that. And
Thank
If you have
so much.
recorded it, can you send me a link to the recording also?
Sure.
I will do that.
Okay. All
Thank
right.
you so much.
Have a good day. And
Thank you.
Thank you.
hope to see you in Portugal someday.
Thank you very much. Yeah.
Indeed, same.
Yeah.
Thank you. Thank you so
Bye.
much. So bye, everyone.